All right. Anybody just have anything right away here off the top here? Connections? Yes, sir.
Well, when the first graph, when it is the
Okay, hang on here, Mitch. Everybody getting this? Okay, go ahead.
the local minimum,
When which graph?
the top one, the red one.
The top one.
Yep.
Okay.
And you go where like above the negative 1.6 where the local minimum is, that correlates to the local maximum of the F double prime graph.
So where this one has what looks like a local minimum, this seems to have a local max. Okay. All right. Richard.
Like on for the interval -1 to 1, they had like opposite outputs.
So like this graph's going up like through here, and this one seems to be kind of going down.
And they have like pretty much exactly opposite outputs in the rear.
Okay. All right. Yeah, man.
Where the inflection point is on the F graph, the F prime graph crosses the x-axis.
So about there. Inflection point on F seems to be where this one crosses the x-axis. There's an inflection point. There's the inflection point. Looks like that. There's the inflection. That's a really good one right there. Let's expand on that. What happens at the inflection point? Well, but I mean, what does it mean? What happens on the F graph? What happens on the F graph when it has an inflection point? Changes concavity, right? That's what an inflection point is. Changes concavity, right? So right here, it's changing from what to what? Concave down to concave up. What's this graph changing? The F graph, the F double prime graph. Uh-oh, each one.
From negative to positive.
Negative to positive. Interesting. When this graph is below the x-axis, now let's look at that because that's, when this graph here is below the x-axis, right through here, isn't this graph concave down? When this one is above the x-axis? Because that's really what happens. When this graph crosses the x-axis, it's changing from positive to negative or vice versa, right? Interesting. Hold that thought. We're going to be talking a lot about that same kind of idea, but with F and F prime today. Okay? So good. So let's talk about the homework in the book first. Any questions? Pretty short, and you might have found it fairly easy. But as I talked with a few parents and I've talked with some of you, one of the things you want to do, especially if you're looking to improve your quiz score from last time, or continue to do a good job on the quizzes, is make sure you really understand the concepts and can answer questions that might seem a little bit different or might seem phrased in a way that may be confusing. And if you really understand the concepts, then I would say that it won't be as confusing. I mean, I'll be really honest. Some people say they don't test as well, or they get nervous, or they don't, whatever. And I'm not saying there's not something to that. But I also think you will tend to have less test anxiety and be less nervous on a quiz if you really understand what you're doing, right? I mean, I'm a track coach, and I've always told my runners that if you get really nervous, or if some nervousness is just going to be natural. You're just going to have it. But if you know you've run hard in practice, if you know you've gotten yourself in the best shape possible, if you know you've worked harder than that person next to you on the starting line, then you're going to be less nervous and you're going to be more confident about what you do. And I think the same thing's true on the test. If you know that you've worked hard on the homework, if you know that when you did the questions and you didn't just say, well, I kind of get it, or I just want to get it done so when it comes around I have something on my paper. If that's all you've done, if you've just barely scratched the surface, then you're probably going to be more nervous on the test. Boy, I hope those questions are just like the ones I studied. I hope there are not any that make me kind of think of it in a different way, because I don't think I got them. You're going to be kind of nervous. But if you've really stretched yourself on the homework questions and you've thought about them in different ways and you've you really made sure you understood what was going on, then you're going to be more confident when you take the quiz. Okay? So you may think, hey, this was pretty easy, but any questions? Any questions on this? You want to talk about? Okay. Well, I think there are some. So we're going to look at page 61, and we're going to look at this graph here, 16 through 20. Now, you may very well have all the right answers on 16 through 20, but I'm going to stretch you a little bit here and make you think about these. Now, maybe it's some of you won't be stretching at all. Maybe you've got this, and that's wonderful if you do. All right? But number 16 says, at which point is f prime positive? At which point or points justify your answer? So, why is f prime positive at A?
It's still positive.
Okay, now. Okay, but think about what you just said. So I just asked you, the question was, where is f prime positive? And you said that it's f prime is positive at A because f prime is positive at A. No, you didn't really say that technically. You said the slope is positive, right? So all you really changed there was f prime and slope. But they're the same thing, right? F prime and slope. So I can't say that, I can't say as my reason that f prime is positive at A because the slopes are positive at A. Right? I got to say something else. Okay? So tell me why. Why are the slopes positive at A? Because okay, Brittany, say that again. It's increasing. She said something very bad there. Now she doesn't. No, that's awesome. That's perfect. That's perfect. Except here's the bad thing, and I promise you, I'm going to say that bad thing like 15 times today. Okay? She said it's increasing. Okay? What is that graph? The what graph? That's the F graph, right? So say it again, because, there you go. Because F is increasing. Because here's what we're going to talk about. We're going to be talking about when F prime's positive and when F prime's negative, and we're going to even talk about when F prime is increasing and when F prime is decreasing, and that's different than when F is increasing. So I will do it many times today. You will do it. I'll try to correct you. You correct me when I do it. Okay? We want to not, and when on a quiz, we write our justifications, don't say it. Okay? Say F is increasing. Say F prime is positive. Okay? We got to really be careful with that. On the AP test, they're very picky about that. Okay? So, at A, F prime is positive because F is increasing. He did it again. Okay? And the same thing at D. You're right. And I know better. I've been teaching this for 15 years, and I still do it. So you're going to do it too. But at D, F prime is positive because F is increasing. All right. That's what we want to say. And today is all about connections between F prime and F. Okay? So therefore, now here's what I mean about stretching yourself a little bit. So when you do that homework question, you might say to yourself, well, what about when F prime is, when are the slopes negative? Where on here are the slopes negative? B and C when F is decreasing, right? And again, that just goes back to Algebra 1. Graphs that go up have a positive slope. Graphs that go down have a negative slope. Okay, that's all we're saying on 16. All right, 17. Between which points does F have a stationary point? Yesterday we defined stationary point to be what? The stationary point of F is?
When F prime is.
When F prime is 0. Now that is a local max min and stuff of F, but by definition, the stationary point of F is when F prime is 0. That's how we want to think about it. When F prime is 0, we mean its output. F prime's output, y value. When F prime is 0 or when the slope is 0. And that happens between where and where? A and B, C and D. One's a local max, one's a local min, but they could have a flat spot, right? So we just want to say when F prime is 0, that's a stationary point. All right. Between which points does F have an inflection point? B and C. Why? What happens at inflection point? Concavity changes. Now you don't have to be specific. It could be vice versa. You could say a good answer would be between B and C because somewhere between B and C, the F graph changes from concave down to concave up. It's also good enough to say the F graph changes concavity. That's okay to say that. All right, so there's an inflection point in there. All right. Now, 19 and 20 now. There's more to 19 and 20 than I think you guys probably are thinking about. Between which pair of labeled points is f prime increasing? Now, if you looked it up on the back to double check yourself, fine. But I think if you didn't look that up, I think there would be a handful of people who might say, let's see, f prime increasing. No, I'm thinking about I'm thinking about number 20. Never mind. And you couldn't look that one up, so we'll see how we did. But between which pair of points is f prime increasing? What did you say?
C and D.
C and D. Why? Now, what's now?
F is F graph.
F is changing concavity between C and D?
No, F is
It's
changing.
approaching zero and then getting more positive there, right?
F is
Becoming less negative.
Okay.
And then becoming more positive.
Ryan, say that again.
Becoming less negative.
What's becoming less negative?
It is increasing at
What is?
F graph.
F graph is what?
Increasing at a slower rate than increasing at a
Now, I don't think you mean the F graph. The F graph's decreasing at the beginning. You said increasing.
slope.
Slope, there you go. The slope of F is, say it again.
Slope of F is getting less negative,
Okay?
getting more positive.
And then getting more positive. Okay, somebody else. Some other people are saying some things. Are you agreeing with that? You're agreeing with that? Go ahead.
B and C could be considered such as well after the inflection point.
Okay, so we couldn't say between B and C because we don't know where the inflection point is. But you're saying, so what you're saying is if we knew where the inflection point is, right, that B and a half, B and a half, is there some, what's between B and C? But B and a half. But somewhere in here, wherever the inflection point, so the answer to number 19, where is f prime increasing, would be somewhere from the inflection point this way. So you're saying when it's concave up? That's what you're saying? You seem to be saying. You seem to be saying that when f prime, let's think about what we just answered there. You seem to be telling me that when f prime is increasing, f is that what you're saying? Because what Ryan said is the slopes here are negative, but getting less negative, less steep, right? And then they become zero, and then positive and getting, if we were to put some numbers on those, the slopes back here seem to be, let's just call that -2, -1, 0. Would that make sense? So these would be our slopes I'm talking about right now. And then they're positive and getting, isn't that by definition increasing right there? Yeah, so f prime seems to be increasing. There's two ways to increase. We talked about this. You can be negative and get less negative, or you can be positive and get more positive. Well, doesn't that isn't that what concave up does? Concave up is either negative slopes getting less steep or positive slopes getting more steep. Interesting. So, what do you suppose if f prime is decreasing? Wouldn't that be concave down, probably? F would be concave down. What you have are positive slopes that are getting less positive, 3, 2, 1, 0, or negative slopes getting more negative. That would be decreasing. Oh, interesting. So, okay. We're going to put all this together. We're coming up with all kinds of interesting connections here. We're going to organize this and put this all together. So you don't worry maybe about trying to get all this thought through. All right. Now, between which pair of labeled points does f prime have its minimum value? I've heard C and D, I've heard B and C, and I've heard back here. So we're all over the map here. Where does f prime have its minimum value? I think it is right there. Okay, do you get that? Now, let's think about that a minute. F prime, okay, those are slopes. Slopes have a value. Now, it's possible that the slopes are all positive, right? Let's talk about minimum value for a minute. Minimum value means the littlest value. Now, if all the numbers are positive, what's the littlest value? The one that's the least positive, right? If you've got a bunch of numbers that are positive, the littlest one is the one that's the least positive. But if you've got some numbers that are both positive and negative, what's the littlest value? The one that's the most negative, right? I don't even know if most negative really is a real term. I don't know. It just makes sense to me, so that's what I mean. But it's the one that's the most negative, right? Now, so we're talking about f prime, which are slopes. This thing has some positive slopes and some negative slopes, doesn't it? So the littlest value of the slopes has to be the one that's the most negative, right? And the one that's the most negative, where it's the steepest going down, would be at that inflection point. So between B and C. Okay? That's how I would think through that. All right, a lot of good stuff on 16 through 20. And maybe you know, have that all thought through and maybe not. But there's a lot of stuff there. All right, let's take a look at that worksheet, because the worksheet helped us to gather some information, just like what we're talking about here, and put it in somewhat of an organized way, and then we're going to write down the result of what we saw in that worksheet. So, we need a presenter here. Natalie. You've been the presenter lately? No? Okay. You're up. So, get out of that and go to the home screen. We don't need to save it. We don't need to save it right now. And go to your documents, and let's open up the first derivative test one from yesterday. Everybody's got that, right? Everybody's got that. All right, first derivative test. Zach, I believe it's on. Okay. Now, you know, and you can look, you could follow along or not follow along, whatever. Now, somebody in the other class said that if you just use okay, go to the next page, or the next page. Yeah. All right. So anyway, when we get to the back, I guess is where I'm thinking. All right. So everybody's got the worksheet, right? So now, the bottom of the worksheet on this page, oops, let's go back.
Oh,
Yeah, go back to 1.2. Go back to 1.2. I'm sorry, I was thinking about that. And then okay, so we'll just run through this quickly. But, all right, critical point. Critical point is where the derivative is 0 or undefined. Okay, one or the other. So, why is this a critical point at x equals 3? Slope is 0. All right, slope is 0. Local max, min, or neither? It's a local min. Where is the slope positive? Greater than 3. Negative 3, or excuse me, 3 to infinity. Now, when you write this, because this is a big part of our next quiz, and your homework the next couple days. Where is f prime, the slope, positive? You would say it's from 3 to infinity. Now you could say greater than 3. Do not include 3. Now it's not wrong if you include the 3. But just as a habit, when we're talking about where is it increasing, where is f increasing, or where is f prime positive, or where is f concave up, when we're answering those questions, giving intervals where it is, we just won't include the endpoints. Just as a habit, we just won't include it. And on the AP test, that'll be fun. You probably get more in trouble including things when they shouldn't be than the other way around. Okay, on these type of areas. Yes.
So you want us then to, you don't want us to just go by what the graph shows, but all the way over to infinity?
Yeah, on this one, I mean, most of the time it's infinity. If I give you a graph in a box grid and it just goes from here, I'll usually try to help with everything. Yes, thank you. That's right. Negative infinity to 3. All right. So that's the other part. Where is the slope negative? So give those kind of intervals and that kind of a situation. All right. Go to the next page, Natalie, please. And so, again, different types of critical points. Is this a local max? It's not a local max, so it's a neither. The slope is positive when? we do this. There are some technicalities that, quite honestly, I'm not that interested in right now, and are really not going to be a part of this next quiz. But we get into chapter 2, and later on, the technicalities are more important. Most of the graphs we deal with here in the early stages are not going to have these sharp points. We do a few in this calculator document, okay, but most of the time not. We really should say negative infinity to 2, and then 2 to infinity. Because think about it. What happens at that sharp point? What is the slope? Undefined. So we can't really say the slope is positive at a place where it's undefined, right? It can't be positive if it doesn't have a value. So where is the slope positive? There. Now, we just got in saying a minute ago that when f prime was positive, f was increasing. Now, here's another little technicality. It's correct to say when f prime is positive, f is increasing, because everywhere the slopes are positive, boom, 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 not that point, but everywhere else, at all these points, the slope is positive, it's fair to say this graph's increasing, right? But it's not correct, technically, to say it the other way. It's technically not correct to say if f is increasing, then f prime is positive. Because isn't this graph always increasing? Always. Even at that sharp point, the graph's always going up. But the slope is not always positive, is it? There's a place there where it's undefined. And the same thing is true of an x cubed graph. An x cubed graph that goes like this, oops, I don't go quite that sharp, but this graph is always increasing, even though there's a place where the slope is 0. Because it's only at that one point where the slope is 0. But every point leading up to that is going up, and every point after that is going up. So just because it's increasing does not mean the slope's positive. The slope could be 0 or undefined at one point, but the graph is still increasing. It's a technicality, but it is something that I wanted to make sure you understood. All right, go to the next page. All right, same scenario. So we have a critical point because the slope is 0. It's a flat spot, so it's neither. It's not a local max or a local min. And where is the slope positive on this one? Never. Where's the slope negative? Everywhere except at that spot. The slope is negative everywhere but that spot. It's 0 at that spot. Okay, but it's negative everywhere else. All right? All right, the last page. 1.5. All right, and again, we have a critical point because the slope is undefined. We have a local max. Slope is positive up until that point. Slope is negative after that point. But the slope is undefined right at that. But it is a local max. All right, turn to the back page. All right, now, what the other class told me is as long as you don't drag this, if you drag that thing, then it screws up this. But if you just use the up and down arrows, I wish I had told you, I didn't realize that. If you just use the up and down arrows, you can land right on those x values. But if you drag it, then you get off and then it doesn't work. So anyway, so here we go. So go back to -8. So we'll give you a chance. And, yeah, and you can left arrow too, by the way, can't you? Left and right arrow instead of having to click on it, which is kind of nice. All right, what the heck? Hey, stop. Natalie, go the other way. Go the other way. What the heck? There's no reason we have to go over there. We'll start at the bottom of the table. Okay?
Well,
Uh-oh.
You got the one on the screen.
Oh, you grabbed the screen. There you go. All right. We'll head on back here to 5. While she's going. Okay. So when she gets back there to 5, why is that a critical point? Okay, now, here, no. There's only 2 reasons why something's a critical point. Because f prime is 0 or undefined. So the only things I want in that first column are slope. F prime is 0 or f prime is undefined. So on x equals 5, the slope is 0. That's why it's a critical point. Now, is it a local max, min, or neither? It's a local minimum. It's a local minimum. We're at the bottom of the table now, right? We're bottom going up. It's a local minimum. Sign change. This is the key thing today. Sign change. F prime is going from
negative to positive.
F prime is going from negative to positive. The slopes, this graph is going down, then going up, the F graph, so F prime is negative, switching to positive. All right, and you can see that right on these slopes as she was going along. All right, very important. Scroll back to 1. At 1, what's going on? The slope at 1 is undefined because it has a vertical tangent. Slope's undefined, so that's why it's a critical point. Is it a local maximum or neither? It's neither. It's not a flat spot either, it's a vertical tangent. All right? Any sign change of F prime? What's F prime? It's negative before that point, and it's negative after that point, right? So there's no sign change on that at a vertical tangent. Okay, keep on going. Back to -2. At -2, we've got that sharp point there. Why is it a critical point? Slope is undefined. Local max, min, or neither? It's local max. Do we have a sign change of F prime? The slope is positive, and because it's going, F's going up, and it's negative after. Positive to negative sign change right there. It's a local max. Okay, going back to the next one at -4. And we have a critical point because slope is 0. What is it? Local max, min, or neither? Neither. It's a flat spot. Do we have a sign change there? F prime does not change sign. It's positive slopes before and positive slopes after. No sign change on a flat spot. Okay, go back to -6. That is a critical point because slope is undefined. It is local minimum. Do we have a sign change? Slope on the left is negative, on the right? Positive. Last one, at -8 is a critical point because slope is 0. It's a local max. We have positive slopes on the left, changing to negative slopes on the right. Now, the bottom part then is summarizing the last 2 columns. First of all, it says, suppose F is continuous at a critical point A. So the first thing that is important about this is we know we have a critical point. So we first have to identify our critical point. All right, and we've identified it. And the first column, we told why they were critical points. Either slope is 0, slope's undivided. Then, the next 2 columns, you should see something in those next 2 columns. That is, everywhere column 3 has a local max, what's column 4 say? You see that? Everywhere you have a local max, you have a sign change of positive to negative. Isn't that true? Now, does that make sense? If the slope is positive, it means what? F is increasing. If the slope is negative, F is decreasing. Does that make a local max? I mean, that's what a local max, that's what it has to happen to be a local max. This is why we never have local maxes at endpoints, because we have to look on both sides. Positive slope to negative slope has to make a local max, even if it doesn't have a smooth curve, even if it's a sharp point. And everywhere, and so, if F prime changes from positive to negative, you have a local max. Next one, if F prime changes negative to positive, local min. If the slope's negative, it means F's going down. Then it switches to positive slope. F prime switches to positive. F switches to going up. Down to up. Local min. If F prime does not change sign, then it doesn't have either one. Could be a vertical tangent, could be a flat spot, something like that. All right. Here's something you're going to get real good at doing. I can't emphasize what a critical idea we just talked about right there. That you will know and you will talk about for the rest of this year. If I have an F prime graph, right here, okay? Here's what you're going to get real good at looking at. If I have an F prime graph, Now again, we're talking about connections, F prime and F. So I got an F prime graph. Now what you're going to notice, and I don't know if you have to write this down, guys. We're going to write some stuff down. I'm not sure you need to write this. If I've got an F prime graph and it does something like this, I'm going to be really interested in that point, the fact it goes right, crosses right there at -2, right? Because what does that mean? Doesn't that point mean that F prime is 0? Isn't that what that means? When I say F prime is 0, this is the F prime graph. When I say F prime is 0, I'm saying F prime's outputs are 0. It's y values. It's where it crosses the x-axis. That's a critical point. It's actually a stationary point. Let's use that term. That'd be better. That's more specific. That's a stationary point. We'll be real interested in that stationary point. And based on what we just talked about, not only is this a stationary point, but F prime to the left is what? Now be careful. Let's don't say F prime's positive slope, because then we're talking about F double prime, right? I mean, this gets crazy when we start bringing in F double prime. I mean, we really got to be careful what we say. All right? Here, F prime is positive, has positive values. And after has, isn't that the sign change we were just talking about? Right there, F prime goes from positive to negative at a stationary point. So what do you suppose the F graph looks like at that place? It's got to have one of these, right? It's got to have one of those. That's a local max. And it'll just become automatic for you. When you look at an F prime graph and you see it go boom, boom from here, from up above to down below, you'll go, hey, that's a local max right there. And when you see an F prime graph do this, at 5, you're going to say, hey, that F prime just went from negative to positive. That's a local minimum. And if you see an F prime graph do this, that is neither. That's a flat spot. Right? Because F prime just went from positive and stayed positive, so F must have been increasing and then kept increasing, but it did hit 0 just for a second. So F prime is 0, so it is flat. It does have a 0 slope, but it was increasing and then kept increasing, right? And there you go. So that's something that we are going to see. We're going to do some graph matching today, where I'm going to give you some F prime graphs and some F graphs and have you match them up. And you're going to use this kind of, you're going to have to think through this information. All right. So that's kind of where we're headed with this thing. Okay. All right. So now, let's write down a summary of what we just learned. And this is in your books on page, it's something like, you don't even have to look it up necessarily, but it's on page 59. I'm going to word it just a little differently than they do. But this is, just like the name of your document, this is called the first derivative test, right? That was the name of your document. Now, why is it called a test? It's a test for a local max or a local min. It's a test to see if a stationary point, a critical point, is a local max or local min. All right? So, we start with this. Suppose x equals a is a critical point of f. Now, another way of saying that would be, suppose f prime of x, f prime of a equals 0, or f prime of a is undefined. Right? Because that's what a critical point is. Now, I think your book just talks about stationary points, but just be true. So, suppose x equals a is a critical point of f. Is it the same as saying suppose f of a is 0, or f prime of a is 0, or f prime of a is undefined? All right, so again, first important element is we identify that it is a critical point. Now, remember that trig stuff we did? We had to solve those trig equations, right? We had those trig equations equal 0, and we had to solve them. Why? Because this. If I give you a function f, and then we're going to learn how to do its derivative, and so now you'll have an equation f prime, and I want to know where its critical points are. Because I want to know where its local maxes and mins are. So what I need to do is I need to take that f prime and I need to see where it equals 0. So I've got to take that equation, set it equal to 0, and I got to solve it. Now sometimes I got a calculator, which I can just go in and let it do it, or sometimes it's no calculator and I got to be able to solve it. So when we were getting those answers like pi fourths and 5 pi fourths, those are our critical points. That's why we have to be able to solve those equations. All right? So first we identify that we have critical points. Now we want to test to see if they're local max and mins. Well, there's two situations. If, and I'm going to put this in a little more easier language than what they have. If f prime goes positive to negative at x equals a, now what they say is if f prime is greater than 0 to the left, and it's f prime is less than 0 on the right, okay? But basically what I mean, we know we're going left to right. What I'm saying is if f prime goes from positive to negative at a, then f has a local max at x equals a. Isn't that what we said a minute ago? All right. Now sometimes I'll write that out and say if f prime is positive before x equals a and negative after x equals a. But you hopefully see what I'm saying. If it goes from positive to negative, you get a local max. And of course, number 2 then, if f prime goes negative to positive at x equals a, then f has a local min at x equals a. Now, in this matching activity we do, that would be a good way to match up these graphs. I would look at it, if you got some f graphs and some f prime graphs and you want to see if they match, then why not look where f prime changes from positive to negative and see if that corresponds to a local max on the f graph. And likewise, if f prime goes negative to positive, which of course all happens at the x-axis, doesn't it? So whenever we have an f prime graph, we're really interested in those x-intercepts, because those x-intercepts are where f prime is 0. And that's where it makes these changes from positive to negative and so forth. All right. So that's called the first derivative test. All right. If we look at page 56 in our book, make sure I haven't skipped something here. All right. If we look at page 56 in our book, I want to say one more time this thing about increasing and decreasing. All right. A function is increasing if its y values just continue to get bigger. But like x cubed, it could level off just for an instant, have a flat spot, and keep going. It's still always increasing. All right? But a horizontal line would not be increasing, right? Because its y values are not getting bigger. Now, they also talk about a term, they say non-decreasing. Now, let's think about that. Isn't non-decreasing just increasing? Yeah. See, a horizontal line is non-decreasing, but it's not increasing, right? So again, a technicality there. But non-decreasing is not the same as increasing, all right? So a horizontal line would be non-decreasing. There's a term they use, monotonic. A monotonic function means one direction. So a horizontal line would be monotonic. X cubed would be monotonic. A graph that's not monotonic is one that both increases and decreases. So anything that just stays one direction, okay, is monotonic. So you may hear that term from time to time, and you want to just make sure. Now, on 57, they talk about that thing we talked about. At the top of the page, they say, hey, if f prime's positive, then f's increasing. But it's not the same to say it the other way. Matter of fact, if you look at how they word it, it's this. At the top of the page, they say if f prime's positive, then f is increasing. If f prime's negative, less than 0, then f's decreasing. Okay, so that's what we're talking about. But now go to the bottom of the page. It says if f is increasing, this is the fact in the box at the bottom of page 57. It says if f is increasing, then f prime is greater than or equal to 0. Okay, so again, that's what it says. If it's increasing, then the slope has to be positive, or it could be zero. It could flatten out. All right? And then if f is decreasing, then it's negative or zero. And so, again, just a little bit of the technicality. And that is only if these are continuous nice functions, assuming we don't have any breaks or sharp points or things like that. Of course, then the derivative is undefined. Most of these problems in your book are not really going to talk about sharp points, so we're not going to worry about those too much right now. All right, one last thing that we're going to write down, and I'd like for you to write down in your notes here, is connections. Let's summarize, let's organize our thoughts here on everything we've been talking about. Connections between f and f prime. Connections between f and f prime. All right, let's jot this down. Connections between f and f prime. What have we said? Well, if, and we're not going to worry about undefined right now. If f prime equals 0, then f is a what? Well, yes, what do we call it? Stationary point. Now, again, this is just to summarize for myself. I'm not going to get real technical with this. What we really mean is at a point A, at some point A, f prime is 0, has an output of 0. Then f has a stationary point at that point. Now, it can be one of three things then, right? It can be a local max, it can be a local min, or you could combine those two and call it local extrema, or it could be a flat spot. Now, that doesn't include vertical tangent because that would be a place where the derivative is undefined, or a sharp point, right? So those are ones that will come in later on. For right now, we'll just kind of go with this. All right, so that's a big one. That's the main one right there. We're really interested in those points because those local maxes, local mins are really things we want to know about. All right, if, what else have we said? If f prime is positive, what? F is increasing, right? If f prime is positive, f is increasing. And so what are you supposed to read? F prime is negative, f is decreasing. They're just so, and then when we throw in f double prime, man, there's just so many of these things that it's really easy to kind of just get it all jumbled, all right? All right, now we might throw in our first derivative test here. So we've got it. So those are three things that can be. Its outputs can clearly be 0. They can be positive. They can be negative. I mean, those are the three outputs you can possibly get. Now let's talk about this changing business, and we'll just really shortcut this. If f prime goes positive to negative, f has local max. I didn't shorten that a whole lot, but a little bit. Okay? That way we get it all in here together. And if f prime goes negative to positive, f has local min. Right? Okay, that pretty much is everything from positive and negative. I mean, you could say if it doesn't change sign, then you have a flat function like that. I don't think we need to put that in. What about the one we talked about in number 19 today? Their homework. If f prime is what? Increasing. Right? We don't have that anywhere here. What that tells about f? F is concave up. Yes, because that means the slopes are either negative and getting less negative, and you might even draw that off to the side, negative and getting less negative, or positive and getting more positive, like -3, -2, -1, 1, 2, 3. That's increasing. Slopes are increasing. That makes concave up. And likewise, if f prime is decreasing, f is concave down, which would be like -3, -2, -1, and oops, +3, +2, +1, -1, -2, -3. So decreasing, positive and getting less positive, or negative and getting more negative, that's concave down. So if slopes are decreasing, concave down, F's concave down. All right, and then the last one really would be the change then of 6 and 7, and we talked about that. If f prime, now, so if f prime goes from, look up here now, if f prime, let's just go from 6 to 7, if f prime goes from increasing to decreasing, picture that now. If the f prime graph goes increasing to decreasing, which would actually be a local max on f prime, right? Then what do you got on f? An inflection point, because if these two change, then these two change, meaning concave up to concave down. And for an inflection point, it doesn't matter which way it changes, right? So we can put in a vice versa and just write this once. So if f prime goes increasing to decreasing, or vice versa, f has an inflection point. Because f changes concavity. Wow, a lot of connections right there. Okay? And everything we've talked about with the increasing, decreasing, local max, local mins, flat spots, concave up, concave down, flex points, it's all contained right in there. Now, you can see where you can, if you use it, you can really get confused because here we got f increasing and decreasing. Well, that relates to f prime being positive, negative. Here you got f being concave down, concave up, but that's when f prime is increasing, decreasing. Big difference. And so it's kind of like somebody said earlier when we talked about this. You talk about the slopes increasing. That's different than if the values are increasing, right? I mean, there's a big difference there. So you really have to be careful. If you talk about the slopes of f prime, what are you talking about?
Value of f.
You're talking about f double prime. You're talking about the value of f double prime, aren't you? Right? The slopes of f are the values of f prime, and the slopes of f prime are the values of f double prime, and you really got to keep that straight. All right. It'll get easier as we go along. Very good. Those are the connections between f and f prime. So what we have left to do today